Hello, this is Guang Zhang. I'm the product manager for IxNetwork routing and switching as well as MPLS segments. Today I'm going to introduce a brand new technology called segments routing. Segments routing is applicable to ISIS, OSPF as well as BGP. But in this particular release, we choose ISIS to be the first protocol to have the segments routing capability. The segments routing is fairly new. It's innovative, so I need to spend a little more time than what was allocated half an hour. So the time for both the technology review as well as the demo may exceed in 30 minutes, so bear with me. The segments routing is still in draft state right now. I'm expecting it will become a standard in the next couple of months. It's pretty much driven by Cisco, leading by Cisco, and with some other complexes such as Alcatel-Lucent and Ericsson, and follow right after. Basically, it's all about selecting traffic engineering path from the source to destination based on either explicit path or using some kind of constraint-based shortest path first algorithm. But it's done in a much simplified way. We'll see how it's done in more detail in the next 10-20 minutes. It's a little bit unlike LDP and ISVPT, for which is, as you know, there are signaling protocols for MPLS networks. The path selection for these protocols was based on hop-by-hop signaling mechanism, and the segments routing is not like that at all. It's actually routing through a segment advertised by these protocols, ISIS, OSPF, or BGP. And of course, these protocols will need to be extended to include label advertisement as well as management. So we're talking about dealing with routing protocols with some extensions to manage MPLS labels. The data plane wise, we'll continue to use the exactly the same procedure as existing MPLS, namely those three major operations: push, swap, and pop. This is no different. So existing hardware will continue to be used as is. The benefit of segments routing via classic MPLS or traditional MPLS, really there's two dramatic benefits. One is simplicity. It does not have nearly as many protocols need to manage because we don't need LDP, ISVP. The routing protocol itself not only do the reachability, but also it can do the labels assignment as well as management. So we have much less protocol to worry about. And of course, when you have much less protocols to operate, then you have much less interactions to deal with. When you have multiple protocols running the same network, they have to interact with each other in order to provide precise information for each layer. When the protocols only a single protocol running, then its interaction really cut down. So that's a dramatic improvement, not only in terms of the CPU resources, but also the overall complexity. Because it's simplified, the automated fast reroute is possibility, or actually with much simple ways. Yeah, as compared to fast reroute in the sense of ISVPTE, where it's very complex with so many protocol extensions just to manage a fast reroute for failure protection. But with segments routing, this gets much easier because it could be as easy as insert adjacency label and route the traffic through the backup links when its a failure occurs. The second advantage of segments routing is the ability to scale. The reason why it's able to scale in such way is because we are not using LDP or ISVP. So we avoid millions of labels in the LDP database or the ISVP network. We just avoid those complex database. And also from administrative point of view, because you don't have that many LSP labels, and then you don't have to configure the labels, these LSP paths. So these are the dramatic benefits using segments routing. Moreover, segments routing is SDN, software-defined network ready. It offers the possibility for smooth interaction with the controllers, such as the PCE, path computation elements, or even OpenFlow controller. So it's ready to be integrated with these controllers. It offers perfect integration with the application, which allows simple and higher programmable. And if you remember, if you know it, the cornerstone for software-defined network is the ability to program network. So the segments routing offer this possibility, and of course has a high efficiency and guarantees the service layer agreements. Because of this, the state of the network, the state is no longer within network, but in the packet. When you decide what packet going through which path, the state of the network is actually resides in the packet, not the individual nodes in the network. Segments routing is actually revolutionary. Per Cisco, they view the legacy of classic MPLS up to this point is equivalent to the ATM of 1996. It's basically from that point of ATM is matured by 1996, and it continued to thrive for a few more years, but to a point where IP took over. And if you look at the segments routing, it's really comparison to the state of ATM. Now, with the new segments routing, it's considered a new generation MPLS. It's really designed for the SDN 2014 beyond. And if you look at these specific characteristics of network features and the segments routing is much better equipment compared to the legacy or classic MPLS. That's why this technology is very new and revolutionary, and everybody needs to get knowledge about what the segments routing. Now, go to the more technical side of it. Segments types. When we talk about segments routing, then what are the types of segments? The very first one is the prefix segments. Prefix is just like the OSPF or ISIS and BGP route advertisement with a certain mask bits. So it's a segment associated with the prefix. When the a node announce or advertise a prefix, you could advertise the same prefix from multiple paths. It's considered as an ECMP, equal cost multiple path. So the segments routing is automatically capable of handling ECMP. The prefix segments is considered global segments. It's global uniqueness. All the nodes in the network is actually aware of the prefix segments. They are unique across the entire network. Therefore, it's global. Slight variant of the prefix segments called node segments. What that means is a segment corresponding to a node loopback/32 address. So it's really a sub-case of prefix segments with the intention that it's really intended for the loopback of a certain router. We'll talk more in terms of the prefix with a value V or N bits in the next couple of slides. The third type, or the second type is called adjacent segments. It's really intended to steer traffic onto a certain adjacency along certain lengths. The next slides will show a better diagram. The difference between the prefix segments / node segments compared to adjacency segments is that the adjacency segments is actually considered local. In this diagram, in this slides, I will give you one complete example here. Let's say the network composed of multiple nodes A, B, C, D, Z. Z will advertise to all the nodes in the network, basically with the segments ID, SID, node SID, 65 to all the nodes there. And this can be done easily with ISS TOV extensions. There's a certain type, IPv4 or IPv6, even some other types. We'll see more details later. Assuming the SRGB, the SRGB is a second-order global block. It's a terminology we'll introduce in more detail later on, but just say a range of these labels. Every node in the network will reserve a unique range of SIDs. So assuming they are very much the same, then all the nodes in the network, when receiving advertisement from node Z, it's going to install 65 into its forward information base. Once installed, node A will do push 65 into labels. And the node ID, the MPLS labels, they are direct mapping to each other. So the node B will know also to reach Z, it's going to use label 65. So the B will simply do a label swap in packets with label 65, which was inserted by A. B simply just do a swap. So does C, because it knows exactly how to reach Z. And it's a 65 in, 65 out, a simple swap. Node D will simply do a pop because it's next to the last node. It's going to pop the labels so that Z will receive the traffic without any labels. In this topology, it's basically there's a single segment. That's why it's called segments routing, because Z will advertise, say, all the nodes in the network in order to reach me, use label value 65. This is a single segment from A to Z. And each node along the way will just simply do the MPLS operations based on the information advertised by Z. Now, a different type of segments called adjacency segments. What it is actually basically for traffic engineering to steer traffic via a specific link. In the example here, we want the traffic to reach from A to Z, for example. It has to go through link CO. It may or may not be the best, shortest path from A to Z, but because the bandwidth requirements or whatever reasons, we really want the traffic to go through that link for whatever purpose. So in order to do that, C and O will advertise each other the adjacency labels. So in this case, O will advertise C, say, use label 9003 to reach me via this link, this adjacency. What the C, when the C receives packet from B, it will insert 9003 label. What that means is detour the path to follow the interface C and O. The advertisement, again, can be done easily with the sub-TOV type. C and O are the only nodes that will install those the adjacency local value into the forwarding information base. The rest of nodes just listen to it, and they may be put on the routing information base, not the forwarding information base. They are two different databases. So if you look at from a lot of perspective, it's what essential it is by having adjacency segments introduced. It actually breaks up the original single segments from A to Z into 3 segments. The segments, 2 node segments, from A to C and O to Z, and the 1 adjacent segment C and O. So that's where you see the segments routing come into picture. It is basically from A to Z. We know we have to go through C and O. So from A's perspective, his job is to make sure the traffic has to reach the ultimate, the destination of C. Because from node C, they will steer the traffic to a different link, not to the ultimate path of Z, but the intermediate path C. So the segments A, B, C is one segment, C and O is the next segment, and O to Z is other segments. The routing is done through segment by segment. So the A, if it knows all these labels or the SIDs to the destination Z, it's going to insert all these labels, including how to reach C, which is label value 72. How to go from C to O, follow through a certain link. It's going to use 9003, and finally, the labels to Z will be 65. So the B along the way, just because it knows how to reach C, and label value 72, so it's a swap top value by 72. Keep the rest, keep the other labels intact. Going to C, it says, okay, reach mean, the top label lost the meaning, and it's going to be push the traffic with the 903, direct the traffic towards the CO link. And then once it's reached O, it's going to say the adjacency label lost the meaning and pop it up, and from that point, OPZ will do similar operation as if from A to C. Due to time to market constraints, there are quite a few TLVs supported by the standard, and we choose to support a majority of them after consulting with our partner Cisco. It's less node SIDs, including IPv4 v6 as well as the multi-topology v4 v6, and for the moment we choose leaving multi-topology IPv4 for future. Similarly, for adjacent SID, there's quite a few different types there, and we choose to implement most of them except the inter-S one. A lot of the key concept for the segments routing is called SRGB, Segments Routing Global Block. What is it? It's a range of SIDs indicated by the start SID and the count 2 values. It's configured on the router by admin or by some other protocols, which is out of the scope of the segments routing. The prefix SID will be derived from the index to the neighbor's SRGB, and this will be more clear after seeing next page. It's basically each node will derive the SID or ambiguous label value out of the SRGB based on the starting value, which is the base, and the index into that the array. So the prefix mapped ambiguous label resolution. The ambiguous label is again just using the SRGB starting SID plus the index. This example here, let's say the right-hand side, which is downstream node, will advertise to the left-hand side node, is upstream node, upstream router. It says Okay, in order to reach prefix 100.111/32 with index 25, and my SRGB array looks like starting value of 6,000, which is base value, the count of 1,000. It's going to have 1,000 values being reserved from 6,000 all the way to 6,999. So the downstream node will advertise to the upstream nodes in this case, okay? So in order to reach prefix 100.111, it's going to use label 6025 because the index was 25, the base is 6,000. It's a base plus index. So the upstream router sending traffic destined to the prefix 100.1.1.1, it's going to use MBOS label 6025, send the traffic downstream. That's how basically it works. Now, its more complete example is multiple nodes in the network. Start from the rightmost. Again, the same example, we're going to advertise at SID base 6,000, count 1,000, prefix 100.111 occupying index 25 to the nodes in the middle. The nodes middle can choose to have either the same base value and count or the same base value and count or different base. In this case, it's actually a different base value, 16,000, or the count of different count value as well. So this node, the middle node, will advertise its starting value and the count to the left node, and as well as it's going to receive an SRGB advertisement from the rightmost node. So it knows, okay, in order to send a prefix 100.111, he is going to send in the traffic with 6025. The TX label towards the downstream is 6025. However, when it's receiving traffic from its upstream neighbor, it's going to expect labels from its own database, which is a 16,000 base and index 25. Okay, so work along this way, all the way from the downstream to the upstream. So basically, if left-hand most nodes, assuming it's just receiving, just say I want to send traffic to prefix 100.111. It's going to use the label 26025 because its immediate neighbor, the base value is 26,000. Okay, it's with index of 25. It's going to send MBOS labels 26025. So the node receiving 26025, it's going to just say, okay, it's intended for me, and I'm going to send this labels out with different labels because my downstream node told me they are using different base. So I'm going to translate that, swap the labels into 16025. And similarly, the node right in the middle will do the similar thing, the swap out the label, because when it's receiving traffic from the upstream, it's expecting label from within its own SRGB base. But when it's sending traffic to the downstream node, it will have to use the downstream node's SRGB base and the index. Look at the Wireshark capture. When we configure the SRGB from the Ixia GUI, you see the starting value 2000, a count of 10, index value 1. The 2010 will be encapsulated in a ISIS pack, the TLV called router capacity. You see the range thin as SID label starting value, as well as the index is actually for each prefix advertisement is going to indicate which index within that range should be used as the MBOS value. Another example is the downstream nodes have the need to send multiple ranges and these ranges may or may not be continuous. For example, in this page, it shows you there's 3 ranges advertised by the downstream neighbor. It has a range of 1, 2, 3 with a total different starting value, maybe different count. These have applications for the different range for whatever reasons. When the upstream node receive multiple ranges advertisement, it's going to concatenate it into a single array. So the index 0 for the new array refers to the very first value of the range 1. The index 99, in this case, refers to the last value of the range 1. But index 100 will be referring to the first value of the second range. So it's indexed it's always kept linear, incremental, regardless what value being in the starting value for different ranges. It's pretty simple. Mathematically, it's pretty simple operation. A few important flags for the node prefix add SID as well as adjacency SID. These flags will be used for different applications. Talking in depth about these, what these means will be beyond the scope of today's presentation. Let's just focus on the 2 important flags. One is N, the other is V. N is meaning it's a node flag instead of a prefix flag. Basically, the advertised is a /32 representing a loopback address. So if you advertise a loopback, you need to toggle the N bits to be on. In some cases, the index to add an array is not good enough. We want to advertise a prefix or node SID with a specific MPLS label. In that case, you can toggle the V value, and then the index or SID entry will contain a real MPLS value instead of the index to a certain array. Similar for the adjacency SID, there's a bunch of flags we'll just quickly pass through. Just be aware. The configuration steps, I'm going to show you in detail during the demo, but generally speaking, you need to enable ISIS, enable the segments routing within the ISIS. Then once segments routing is enabled, it's going to automatically enable the white matrix as well as disable the discard LSB. The reason being, segments routing would require the learning info to derive the right MPLS via legacy, or in the traditional ISIS case, by default, when we learn the information, we automatically discard because we don't need those information to build up packet. When you come into the MPLS domain, everything is dynamic, so we need the information from the database in order to build up the packets with the right content. Under the router section, they have prefix or the node prefix simulating loopbacks. You can talk them as node or advertise index or advertise V value. These flags are available. For adjacency, you go to the interface. You can enable adjacency with the different SIDs, indicating a value or index. When we advertise the prefix via network pool, we can actually use patterns to configure those index. Just make sure when we advertise multiple network group, either or IPv4 or mix IPv4 and IPv6, make sure we now step on each other overlapping index value. So the customer pattern is become handy. We'll show you with example. You can advertise IPv4, IPv6 all together or separately. That's it's really up to the user to choose. Now, our solution offers you additional ability to configure a topology. The idea is with topology where we can emulate a large number of network nodes with a specific topology tree, grid, fat tree, ring, mesh, whatever the topology chosen. And each of the simulated routers within the topology can in turn speak segments routing. They can advertise their own SRGB and is with a specific index as well as adjacency. The idea is to be able to simulate larger topology and feed that information to the DUT, that the DUT make decision. The loading info from the ISIS emulated router, it shows clearly the V4 and V6 prefix with the prefix SID derived value. They have base value, you have index, then you can derive the prefix SIDs. Traffic wizard will retain some of either network group as well as the router address or the interface address. Some of the endpoints will be segments routing aware and some of them will not. For example, in this case, the network group represented here as a prefix. Once selected, it will be segments routing aware because it has all the segment routing information available via the interface, for example, IPv4. That will not be segment routing aware because the interface is just regular reachability routes. We'll see those from the demo. Now, one of the caveats, actually not much caveat, not much limitation at all, is that adjacency segments today within IxNetwork we cannot learn and store them. It's not a significant limitation today. The reason being, even if we support that, it's not going to be much helpful because as the head end or the ingress node, we don't do the shortest path first algorithm at all. So even if we receive something from DUT, we will not be able to figure out if the adjacency would be anything useful to us at all, because I don't have an algorithm calculate what's the best path or what's not the best path. Therefore, the information received with respect to certain links is not much useful at all from English point of view. What's more important is we need to test DUT ability to resolve and to calculate the best path, or shortest path with the constraint with a certain adjacency. For example, in the picture here, on the right-hand side, we can emulate a large number of nodes and advertise specific node IDs as well link adjacency IDs so that the DUT will be forced to choose from which link to reach the ultimate destination from the source and the destination. So it's DUT ability to be able to figure out what's the best path with adjacency segments in mind. And this major function, this is a predominant user case, it's not missing at all. It's if you test in X here as the DUT row in this picture, then we're going to have a little bit of trouble to figure out what's the best path. So it's not considered a major limitation, but just something that our customer need to be aware. So in terms of competitive information there, and one of quite a few things that the customer need to be aware when you're choosing a testing solution. What kind of factors you need to look at? Is a test solution easy to scale in terms of number of emulated routers, number of prefix SIDs, and more importantly, in this, because uniqueness of this technology, it requires index pattern to be easily configurable so that we can do different test cases as evident later on when we're doing the demo. It has to support both V4, V6 because the segments routing was invented not just for V4 but also consider V6. Does it support multiple SRGB or just single one? How about the flags? Because all these protocol option flags are important to enable, disable for some of the important negative tests. What if we advertise SIDs with one case index, the other case value? If you have a conflict requirements, how the DUT will react, those are very important negative tests for the DUT. Of course, the solution must offer complete topology emulation, which each of the links, emulated link or simulated links, simulated routers, each of them has to be segments routing capable, so that you can offer a complete topology to the DUT and force the DUT to make a decision going along certain nodes and certain links. Essentially, with this, you can emulate multiple segments with the entire network. Of course, the traffic binding, auto binding, labels, derive the labels from the advertisement and be able to send the traffic with the right labels. That's a basic function, traffic. And also, what if there's a need for the tester to build up a packet with many labels to simulate multiple segments, 10 segments, for example, with a combination of node segments as well as adjacent segments. And the tool must have the ability to craft those packets with as many labels as needed. Each label will represent a segment. So these are all important questions for the customer to ask when they choose a test solution. We're going to have a demo. In this case, Ixia will be emulating 10 ISIS routers. Each of the router will have a different SRGB base, same count 100. Each node for the emulated router will have index 0, and we're going to advise 10 IPv4 prefix index occupying index 1 to 10, and 10 additional IPv6 prefix with index 11 to 20. So it's a total pretty consecutive within the same SRGB. Similarly for the second router, the same index principle, but you have just a different starting value. Similar all the way to 10 routers. The configuration for this must be simple, easy to follow. Now, before I switch to the demo, let me quickly show you show you from the scratch how on a high level the workflow look like, and then we'll show you in more detail how to configure those the examples I provide in the PPT. Just wait for the network coming up, connecting to my demo. Okay, here. Let's see. The workflow is. Let me delete this one. Okay. Add a new topology. Let's select a port. I want to generate segments routing capable routers. So select the protocol you need to select is the ISIS L3. Say finish. By default, we create 10 emulated routers. Click on the ISIS on the very first level. On the router level, let's make sure that we need to enable the segments routing. So once enabled, every single one of the 10 routers will be segments routing capable. And then go to segments routing specific tab to enable those bits, the flags. You can change the loopbacks from default. Default is /32 with 1111 and increments for the 10 routers. And you can configure the node prefix, the node SID to occupy either the same index from different ranges or increment. You can configure how many SRGBs, either one or multiples. For each one of them, if you enter 2 here, you have the starting value, let's say, do a start value, reserve 100, and the count will be 100. So that way you can do very easily do a different base value with the same count or different count, but just make sure that they don't overlap each other. That's how you configure the SRGB base and the count. If you have multiples, make sure you configure all of them, as well as the node SIDs and the index for the node. You can click N, that means the advertising for the loopbacks will be considered as node SID instead of regular prefix as SID. Now, to configure the adjacency, you go to the interface, you can enable, go to the segments routing section here, you can enable adjacency SID and with a specific index or value. If it's value, make sure V is enabled. So that's how you configure the router, the interface. Next, we want to advertise some prefix. Go to network cloud, select either IPv4 or V6 or all together. So each of them will advertise either one or many. And these prefix, you can change the value, make sure they have the starting value, and then go to here to specifically change the segment routing options. The prefix, the index value, and the flags. You can customize in any way you want. It's pretty easy. And of course, you can advertise the topology with, let's say, just a simple grid level. Say OK. And we have emulated 9 simulated routers. And for each of the router, we actually can enable the segments routing on all of them and change the simulated router in a very similar way as the emulated one, with the flags, with the loopbacks, with the SRGB starting value count, index. Everything is manipulable from the GUI. The individual links, the interfaces, very similar. You can enable the adjacency. And each of them can advertise in turn those different values. They can advertise additional routes for each of the simulated routers as if it's a prefix SID. So all these capabilities are there. That's just how it looked like from a very high level. Next, instead of config them step one by one for the sake of time, I config the configuration already, which basically we're going to do exactly something like this. We have 10 routers. Each router will make sure we advertise SRGB with different starting value, the index patterns. All right, coming to here, we can very quickly examine here the router SRGB is indeed enabled on the basic here. It's enabled, and the segments routing, we advertise the loopbacks. It has to be N. That should be good enough. And the SID value for the node segments is actually 0 for all of them. It's index 0. That's just per the requirements. The first index will be consumed by the node SIDs. And then we advertise. The space is just like that, starting value 1000 and increment by 100. So each of the 10 routers will have different starting value. That's just how you configure the router side. Then adjacency, for the interface adjacency, we just enable put different values there. And when we advertise those IPv4, remember we want to take index 1 to 10 will be for. So for the NGPF, it offers a custom patterns. It's very powerful. We start index 1, increment by 1 all the way to 10. Then we'll need to repeat the same index. The pattern is like this, 1, 2, 3 to 10. And then we need to repeat the same index for the next router and until all of total 100 values will be like that. So you in the loop increments by 1, the out loop without any increments so that you can repeat the value. That's how you do the index assignment for multiple routers, not just the router. Remember, we have 10 emulator router, each advertise 10 prefix. So we have total of 100 prefix need to be assigned with the unique index. Similarly for the V6, we have to look at the custom value here. Again, if you look at the assignments here, starting value is 11, increment by 1. And for the rest of the routers, just repeat the same pattern, 11 to 20, do that. So let's run the protocols. Obviously, I configure the partner port, the backpack demo here. The other port just advertise a similar IPv4 routes only, but occupying a different range, which is starting value 2000. The right-hand side will be starting as 1000, and the left-hand side will start with 2000. So we're going to, once the ISS is up, let's examine the loading info from the emulator router. Let's check the very first one, see the loading info here, what we get. For the IPv4 one, we get these prefix. First, we get a node SID, which is occupied index 0. The next, that's the interface, just standard ISI routes without any SID attachment or association. That's fine. The 10 prefix occupy index 1 to 10, and the base is from 1000. So those 10 routes will take these SIDs. So that's as expected. And next, check the IPv6. It occupies index 11 to 20. So it's actually learned correctly. Let's check, just simple check. We have total of 10 routers. Check the third router. It's very similar, but has a different base value. Let's start with V4 here. We advertise different values. You see the starting value will be 1200, but index is very similar pattern. Similarly for the V6 here. So everything makes sense. Quickly go to the traffic. I build a bidirectional traffic. The way I select here is select the network prefix here. If you can check, all of these 100 will be selected and generate traffic from to the other side. Because of back-to-back, I'm able to generate bidirectional traffic. So once finished, let me check my first flow group, which will have the correct values of MPLS value here. You'll see them 1001 to a total of 100. Each have the correct value, correct MPLS value. If you happen to check from the second one, it actually shows MPLS value of 2000. Like I said, we did not show you the configuration detail, but it's start value of 2000 instead of 1000 base. Everything makes sense. So that's about it in terms of technology review as was a demo. And I'm sure once you go through it, you're going to have lots of questions. Feel free to contact me. Let me know what you think. And And if you have any specific questions, feel free. That's it today. Thanks.